welcome back. The next lesson in the video, we're going to show you how you can do design for columns using some of the design aid charts that we have available for us. Now, for design of a column, one of the problems that we face is that there are a whole lot of unknowns that are going. One, I don't know the dimensions of the column, I don't know where the steel is located, and all of those play a huge role into my moment capacity and my axial capacity. And then on top of that, there's this interaction that exists between moment and axial loads that we also have to be aware of and mindful of. That as I change one thing, it affects the strength in the other, and it's a not an easy problem to solve. Now you can set up spreadsheets to be able to tally up these values, and those can be useful for analysis, but for design, it's a lot harder to kind of work with. All right, so I'm going to show you some of the design aids by kind of working this through an example, and I'll kind of explain the chart here in a second as we start to go through. All right, now for us, I'm going to look at a column that has steel in two faces, okay, and we're going to design a column for 600 kip feet and as the moment and 500 kips as the axial load. Okay, this corresponds to an eccentricity of about 14.4 inches. All I'm doing is taking the moment and I'm dividing it by the nominal on that. All right, so that's kind of gives you kind of a sense of the distance that we're talking about for this interaction. Okay, we're going to take f prime c of 4 ksi and fy of 60 ksi. Now before we jump into it, I'm going to pull up the chart that we're going to use, and so that you can kind of see how the information that's laid out. Now, a lot of different sources have different charts, but they're mostly laid out in a similar fashion. But you'll want to make sure that you read fairly closely the requirements and the way the labeling is done. All right. So the first thing that you notice on these charts, and I'll pull this up a little bit so you can kind of see what's going on. We're going to start off with the basic pertinent information. Each chart for an interaction diagram is set up as follows. There's an f prime c specific value, there's an fy specific value, and there's this gamma parameter, okay? And as well as that, there's also the arrangement of steel. So this is the chart that would be for 2 layers of steel. There is another one that is for steel equally spread around the cross section. I don't have that one in this video, but just be aware there's also interaction diagrams for round columns and a whole wide variety of different resources that we have on here. All right, so the dimensions that they call out then, so for us, and the one that you want to really pay attention to is this H dimension. You can see that that's the dimension that's perpendicular to the layers of steel. So this is the width of our section, okay? And then gamma is a multiplier on that H that represents the distance between the bars. Okay, so what really happens is there's a cover distance that has to be included here as we start to kind of look at that. Okay, so depending on what you choose, as you iterate through the process, you can actually move from one table to the next, because if you hold a cover constant, then gamma is going to change. Now in our example, we're just going to work off of this chart and show you what happens relative to the chart, and then you can kind of get a sense of the overall process. But I just want you to be aware of that. The B dimension is the other dimension, okay? And then to give you some idea, the loading on this then is that the bending axis is this center line happening here, and then our load is assumed to be acting eccentric to that. Again, this is going to be at the centroid of the cross section, and this assumes the steel is spread equally between the faces. Okay, so that kind of gives you kind of a layout. Now what you see on the chart then is a series of factors, and I'll try to pull this up so you can see everything. Maybe if I zoom it out a little bit, that might be a good idea. Let's do that. Okay, pull that out just a hair, okay, and so that you can kind of get a sense of some of the values. Now I know the numbers are kind of hard to read, but those of you that are taking the class with me, we'll have this in the packet for you to look at, and for everybody else, you can find these online to give you a better sense. I'll zoom back in on the relative part, on the pertinent parts when we get there. So what happens is basically you're going to calculate 2 factors on this. The first one is Rn, okay, and you can see that that's going to be the nominal moment. That's that Pn times E value, the nominal moment, okay, divided by f prime c, divided by Ag, divided by H. Okay, so the factors that go into this, you're going to calculate that value. Okay, these are what we call a normalized table, because you're dividing it by the strength and dividing it by the cross-sectional dimension. Okay, and that's why all your values are kind of odd acting along here. All right, the Kn factor then is going to be the axial load divided by f prime c divided by Ag. So this is just a straight, almost a kind of an axial stress kind of calculation here, and the ratio of that stress to the f prime c compressive value. Okay, and you can see that those values go up this axis. On this diagram are a series of interaction curves that you see. And you can see that basic shape that we talked about. Okay, so here's my P0 limit, and it comes over, and then it kind of increases down to some point. So row balance for this one is about here, and then it comes back around here. And then there's another one, you get all these kind of concentric rings almost that kind of come around this thing. Each one of these rings represents a reinforcement ratio for the column. The lowest line on here is 1%, that's row G of 0.01. And the maximum that you'll see is up here at the top is 0.08, and every line in between is represented. Okay, and this is because these are the ACI limits for reinforcement in a column. Remember, we saw those, we talked about those back in one of the earlier column videos about the min and max steel that can be put into a column. All right, and this will ensure, a behavior that we're expecting, whether it's ductile or preventing a compressive failure or whatnot, all those kind of things. So those are our curves here. So those are generally the way that we use these design tables. If I can figure out where I am on this axis and where I am on the lower axis on this thing, then I can quickly plot the point and figure out where I am in this diagram. And say I wind up here, well then I'm in between these two lines. Normally I'll go up to the large one, okay, but that kind of gives us a sense of this. Okay, I can also work off of these diagonal, these radial lines, if you will. Okay, and what these are the ratio of E, okay, of my E to my H. Okay, and so we start out, again, remember for concentric, E is 0, so that's the vertical line, and then it goes, this particular diagram goes 0.1, 0.2, 0.3, 0.4, 0.5, all the way around, and you can see that it kind of picks up values. They don't draw all the lines, but you can kind of see the ticks for all the other ones in here. Here's 1.0, okay, so forth and so on. And so you can kind of get a sense of the diagram, where you are. The problem is that if you're doing design, you don't know H. Okay, you'll know E because that's just the ratio of the moment to the axial load, but you don't know H. So I don't know where I am on this in the design phase. That's why a lot of times working with KN and RN and the row values is the much more simplistic design methodology to use. Okay, now, some other information that's kind of hidden on a lot of these charts that's kind of interesting is for all of these row values, this line right here, you can see represents the epsilon T, the tensile strain of 0.005. So if I'm below that line, my phi for bending is 0.9. And then if we kind of look at the other lines, anything above this, you know that phi is going to change based on the yield strain. You're still bound by those same rules that we set up with SRR and DRR. They also include a line here that is epsilon T of 0.002. Okay, so that would be the lower limit on this. So if I'm above this line, then I'm using a phi of 0.65 on the flexure case. Okay, and so that's kind of what's being factored into those. Now, we don't have the fees factored in, but those will be some of the process that we're going to look at. Okay, and then there's some other lines in here that kind of give you a sense of where you are at the stress level. So here is about where the tensile stress is yielding. Okay, here is about where FS is at half of yield. Here is where there is no tensile stress in the steel. Okay, that it's been zeroed out, and so forth and so on. So there's a lot of information in this chart and very little space to be able to working. But again, remember, make sure that you get into the right table, and you've got to watch that gamma value. Okay, now I'll include this picture in the packet so you can kind of see what's going on. They do have some of these in the back of the Nielsen textbook that we've been using for this course as well, and they're pretty common. You can pretty readily available to be able to find. Okay, but again, you've got to make sure you get the right diagram and the right material properties and the right gamma value. This is the guy that changes, and you got to watch him especially because there'll be 4 or 5 of these diagrams that look exactly the same, with the only thing changing is this. It might go 0.7, 0.75, 0.8, 0.85, so forth, and depending on what your gamma is, that's where you're going to wind up. All right, so let's give one a try and take a look at what we have happening here. We'll bounce back and forth between this chart as we look. So as I said, we have a moment of 600 kip feet. We have an axial load of 500 kips. Okay, that gives me an E of 14.4. Okay, and again, we're going to go 4 KSI, 60 KSI, and for now, I'm just going to assume that gamma is equal to 0.7, and that this isn't going to change as I go through my iterations. This is an absolute unreality. Okay, this will never happen. As I change my column size for a constant cover, gamma will change, and it will easily move me from one chart to the next. Okay, but just to kind of give you a sense of what's happening in the values, we're going to focus our attention on one chart, and we're going to make an unpractical assumption of gamma of 0.7. All right, so the first thing I'm going to do is I'm just going to kind of take a guess because I don't have a starting point. I don't know how big a column I need. I don't know I do know that I'm going to do 2 layers of steel, and that was just a kind of maybe it's an architectural consideration, or experience tells me to do that. Again, the arrangement of the steel is a factor, okay? And a lot of times when these loads start getting big, you kind of go, well, maybe I should have steel in all faces because that's a different chart and a different arrangement, okay? This one works very well for bending in only one direction. Notice that if I bend about a horizontal axis here, I got minimal steel out here at the extreme, so it's not as efficient. But if I'm bending about this axis, that's a real good resistance to that particular moment. Okay, so all we do then is we take our 18-inch guess. I'm going to calculate the gross area, which is 324 inches squared, just 18 times 18. Okay, and then just to give you kind of a sense of this, if my cover is 2.5 inches, okay, what we're looking at is this gamma H value. So if this is 2.5 inches and this is 2.5 inches, 2.5 plus 2.5 plus gamma H better be equal to my 18. And that's all I've done is rearrange, and I solve for gamma. And you can see that for this picture, you would get a gamma of 0.72. It's close enough to 0.7. That's kind of giving you a sense of the dimension. So 2.5 inch cover on an 18-inch column will get you a gamma of about 0.7. All right, so all we're going to do then is we're going to calculate these factors, these coefficients. So the first one that we're going to factor is this guy. That's Kn, and this guy is Rn. So Kn is just my nominal axial load divided by Ag, okay, which that's just a stress calculation, becomes 1.54, okay, will get me that particular value, okay, and then Rn is going to get me a Fmn over an Agh, okay, it's going to be 7,200. Again, you got to watch your units, get this guy into kip inches. I'm going to divide that by Ag, I'm going to divide that by then the H of my beam, which is 18 inches, gets me 1.23, and then all we're going to do is we're going to plot. All right, so if I look, I'm looking for a Kn of 1.5 and an Rn of 1.2. Well, you can see right off the bat, my 1.2 on this guy is way off the table. So that size will not work for us. I could get the 1.5, but I'm so close to the maximum limit on the steel, it's probably not practical. And again, I'm plotting a point that's clear over here somewhere. All right, so we're clearly undersized on the beam. So one of the options that we have to manipulate this is I tend to want to try to get this value down toward this bottom line somewhat, because that's the smallest amount of steel and it will ensure more ductile behavior. Okay, so we need to do something to pull this point in. So the biggest thing that we can do looking at the equations is I can play with either F prime C or I can play with Ag. All right, so Ag, I'm going to get the biggest bang for the buck, so that's where we're going to go. So we're going to go take another guess. Right, and again, you're just kind of playing the process, playing the game. Okay, let's try a 24-inch beam, okay? Ag is 576. Now again, we've changed our dimension here. We would technically change our gamma. So if I use a gamma of 0.7, we've now assumed cover is 3.6 inches. Not a huge amount, but it's kind of, again, you're not holding it constant. We would technically probably go to another chart, but for whatever reason, we're going to use this guy again. All right, okay, so repeat the process. Here's my Kn factor. Here's my Rn factor. Okay, and I can calculate Kn in the same way, 0.86. And I can calculate Rn same way, 0.55. Okay, that's the KSI units. Okay, and if I plot that, you can see I'm now at 0.86. Okay, so now I'm down here. Okay, and then I'm also at my moment value that was 0.55, so I pull this line over to about 0.55. You can see we're sitting over here now. Okay, so we're getting closer. We were way out, up here somewhere. Okay, and now I'm here. So we're moving in the right direction, but we're not quite there yet. So we need to go one step further. Now, the way that I'm choosing my sizes, I tend to go in 6-inch increments, right? I started at 18 by 18, and then I went to 24 by 24. Now, again, I'm also assuming a square column. You could play with B and H, but for the sake of this exercise, we're keeping everything the same. All right, so we're at 24, so then our next guess would most likely be a 30 by 30. Okay, so if I go through and I do that, same process yet again. Okay, and plugging in my values, we'll go a little faster. Ag is 900. My Fpn of this guy is 0.55. Okay, and then my Fmn, again, this is Kn, and this is Rn, okay, is now 0.267. Okay, so what happens when I do that then, okay, we're going to pick up our values of 55 and 0.267. So we're going to come up, or sorry, let's go to 0.55. That's a line that is somewhere about here. Okay, so I'm just going to kind of lay that line in just because we can kind of see where we're looking. Okay, and then I'm going to come up to 0.267. You can see, so now each one of these ticks is 0.1, so that's 0.2, 0.6, so this guy is 0.267. You can see that we'd be living at a point that's right about there, if you look at it. Okay, so what that means is that for this 30 by 30 column, the row that I would need would be between 0.03 and 0.04, okay? So that's between 3 and 4%. Now, ideally, I would like to be lower down, but we're going to run the examples and show how you can use this number then to get to my area sizes, and then kind of show you some decisions that we'll make on this. Okay, but again, what I'm going to do is, for strength's sake, I'm going to round up to here. Okay, now notice we are above 0.005, so we would have to correct our phi value in this case, but because I gave you the design load, we've kind of hidden that away, but that could change your number, and that could, again, give you another value that kind of is a moving target, if you will. But you can kind of see that. So again, we're also well up above the 0.02 line, so I know my phi is 0.65 for the moment. Okay, all right. So again, a lot of this is just more to illustrate the process of what we're trying to do. Okay, so once we do that, okay, we know that our row required, this is our row G parameter, is going to fall between that should be 0.03 and 0.04. Okay, the cover that comes with a 30 by 30, again, working that calculation, 0.7 times 30 is 21 inches. Cover then is 30 minus 21 divided by 2. We'd be at a 4.5 inch cover. Okay, and so that's kind of we're getting a little excessive now. In reality, I'd probably want to decrease that, which would change my gamma. It'll actually increase my gamma and move me to a different chart. All right, now for the sake of our argument, we're going to round up to the nearest row value and take a 0.0, that should be a 0.04 on this. We're going to round up just to make sure I have enough steel. Okay, and then once I have that, now I can calculate the actual AS that I need, and that's just rho G times AG. So for this beam, or for this column, it's going to be 0.04 times 900 inches squared is going to be 36 inches squared would be the required amount of steel. And you're looking at this going, oh my gosh, that is a ton of steel. Okay, and that's the thing, these loads are pretty heavy. You had a 500,000 pounds axial acting on this thing. Okay, so what we do now is we start looking at the configuration of the bars. Okay, now, because of the diagram that we chose, again, back on this chart, right, we're looking at steel has to be placed in 2 layers. Okay, I can't put anything in these other faces because we don't know the impact of that on the capacity. It actually adds to it, but this is the minimum of what I have to do. So we're going to stick to kind of the chart that we chose as part of the exercise. So if I did 8 bars, that would be 4 in every face. I could take my 36 inches squared, divide it by 8, would give me 4.5 inches squared per bar. Okay, now a number 18 is only worth 4 inches squared, okay, and these number 18s are massive bars and have some detailing issues with them, but in a column, you could get away with it if you needed to, okay, but for us, I'm going to call this as no good, all right, because, well, it is no good because this is only 4 inches squared and I need 4.5, so 8 bar configuration is out. Let's try a 10, all right, if I do 10, it becomes 3.6 inches squared per bar, okay, and a number 18 is worth 4, okay, we could do that. I could put 10 number 18 bars. I could put 5 in each face. This dimension is 30 inches. I'd have plenty of room and plenty of cover to be able to fit all of those in. Okay. Now, again, if you don't like the number 18 bars, and one of the things that you'll see in some of the serviceability checks is that, cracking criteria and stuff, we tend to like to do as many smaller bars as we can in a lot of situations. Not always, but sometimes. All right. We could go into, we could go a little bit further. Let's suppose that we go when we do 10 bars in every face. Okay, so 10 bars in this face and 10 bars in this face would be 20 bars. And so I could go 36 to 20. That gives me 1.8. A number 14 is worth 2.25 square inches. And you could work your way down to that I could use, a total of 20 number 14 bars as opposed to 10 number 8s. Okay, and then if I go to a number 10 bar, kind of repeating the process, I didn't sketch these out, we could figure out the number that I need. I could do, AS is 1.27 for a number 10, 36 by 1.27 gets me 28.3. I need an even number, so I round up to 30. I could do 15 per face with number 10s and get that, and that's starting to kind of reach the limit that I could fit by the time I get my spacing and those kind of things. So a number 10 doesn't work real well, and so maybe a number 11 is a better choice. At this point, I'm kind of liking the number 14 just for my spacing on that, assuming that everything fits. You still have to check your dimensions, make sure your clear spacing is fine, make sure that you've got your cover and your stirrup and everything else like we checked in some of the flexural problems. But so you want to make sure that we're looking at that as well. Okay, and then just to kind of finish out the exercise, if we use a number 9 area of steel is 1.0, I would need 36 or 18 per face, and I don't think that would fit at all because again, 30 inches, 18 of those 17 spaces is 35. We're going to say this is no good. Okay, because it won't fit. Okay, like I say, 15 would be close, but I'd have to check, but I'm thinking probably this is what I'm going to look at. Okay, now again, none of these options is really all that appealing from a construction and a design standpoint. So what we want to do then is let's take a look and see, what are some of our options for improving that we can do. Okay, and a lot of it has to do with, again, this diagram. Obviously, if I get to a smaller row, then the area of steel that's associated with that goes down dramatically. We were clear up here at 0.04, right? If I get down to this guy, then I would have 1/4 of the steel required of what it was we were designing for in this. And so that would take my 36 square inches and drop it to 9. Okay, now obviously to get to that takes a little bit of effort. And so let's talk about ways that I can pull that number, from where we were here, start pulling it in a little bit. Okay, now we're on this E line, if you will, and we computed E to be about 14 inches. The E to H ratio of 0.5 on this would be 15, so we're right about on this line. We could just pull this line and kind of follow this line down, and we could come into these values. And then you could actually back calculate the AG that's required to prove these. But let's just talk a little bit more conceptually about some of the ways that we can improve this process. Okay, the first one that I would look at is using a different table based on the different distribution of the steel. Okay, like I said, we had a whole lot of space between here and here in which I didn't count the bars in the perpendicular face. I needed those, but we didn't include anything here. And there's a whole lot of room for steel there that could actually contribute to our calculations. That maybe that would help us out. Okay, we could use the same arrangement, but then we could modify our gamma value. And typically, as I increase gamma, the required area of steel is going to decrease. That I increase gamma, the rho G value will start to decrease. Now, it's hard to visualize on this chart because each chart is for a specific gamma, but if I took a gamma of 0.8, these curves would be inset just a little bit. Okay, or sorry, it would be the other way, that the 0.8 would plot a little bit higher, for a higher gamma. Okay, and so what I do is, in effect, I'm pulling that rho G1 value out toward the point that I'm looking for on the chart. But again, that's hard to visualize on this, so it's generally not the most desired approach. You could change the AG like what you saw us do. I could change B or H or both. Okay, and typically as AG goes up, the rho required, that rho G value, decreases. Okay, and again, that's because each of these coefficients has an AG in the perimeter, or in the denominator. And so as I increase AG, Kn and Rn both start to decrease, which in effect pulls my point down here. Now again, recognize that I could get crazy and pull it all the way down to here, but you're bound by the minimum, which is this 0.01. So really we're trying to hit a point that's somewhere around here as the most optimum point for this particular chart. Okay, so that would be kind of your goal. So 1%, 2% would be a vast improvement over what it is that we're trying to do as far as these bar sizes. Okay, but for a first guess to get a sense of what size you would need, that's kind of how we would do it. I take a mid-range row value and I size my column off of that. Okay, and then the last option that you have then is to change material properties. Okay, and generally as F prime C goes up, the rho required will decrease as well. Okay, but again, you're bound by that 1%, and I can much easier change AG than I can F prime C, right? If you're at 4,000 PSI, going to 5,000 PSI wouldn't be as much of an improvement as going from, an AG of 300 square inches to a AG of 600 square inches, doubling it. Okay, so it's a lot easier to increase things based off of this one. Okay, so those are kind of some of the ways that I would start to kind of look at this approach. And that's kind of how these design aids are set up and how they function for us. So like I say, I know it's, a lot of different thoughts are happening in here. I hope it made sense in what we were trying to do. The design aids are really cool for just kind of, if you just need just a rough size, maybe you're building a computer model and you're not worried about the reinforcement yet, but you need dimensions in order to be able to assess the stiffness of the column or the interaction of that column with the frame that is acting in for lateral effects or something. These design aids can be really, really useful tools just to get a quick and dirty, sense of the magnitude of the size I need. Do I need a 12 by 12 column or do I need a 36 by 36? Okay. Now, as you get better at this, you'll start being able to pick up, combinations of, of axial load and of, you know, nominal moment acting simultaneously on a column, and you'll start kind of building this library in your mind, if you will, of being able to, for certain eccentricity, what size did I need to get kind of a sense of the values. So I hope that, like I say, I hope that made sense. Leave us some comments down below. Let us know if there's anything that wasn't clear, and we can address this in a follow-up video if we need to. Otherwise, as always, like our video, please, and subscribe to the channel, and we will see you all next time. Happy engineering.